The final bit of this lecture is looking at another case, in this case PV, which are also very important in the present and future society, specifically if we're looking at renewables and lowering our footprint. Just a quick picture, I'm not going to go in this in detail, a typical compositional analysis shown over here on the left-hand side. On the right-hand side, the exegetic cost for producing this on the right-hand side. The detail of this, you can please have a look in the paper. So I just want to briefly point you to this work to show to you what design for recycling of a product means in its full context. In this case, we are looking at a silicon-based PV, its inflows, its outflows, the flow sheet inside it, and the recycling of kerf coming from the wafering and end of life, and considering where's the optimum for this specific situation. Not only in terms of an LCA type of score, but also the true degradation of quality of materials while it goes through the system, and therefore also being able to give it an exergy cost and dissipation. As I said, very important for you to consider, because this is the real hidden cost behind everything that makes things difficult. Remember to take out the sugar from your cup of coffee and get it out as a pure crystal, not contaminated by coffee or milk. That's what this is about. This requires some detail, and once again, I'm not going to explain these figures. I just want to point you to the fact. Have a look at the detail. To make this possible, you need to have a flow sheet that brings this all together. There are 7 flow sheets in total, which I just showed to you, some of them, which are all linked, which contain the reactors that are required to make this work. From the primary ore to the product, it's recycling, and back again. What does this permit us then to calculate? It's simply you can drill right down to the detail, not only of the carbon footprint, but you can also look at what's the effect of kerf recycling vis-a-vis end-of-life recycling, and where's the optimum. And that's a key message once again. A simulator permits you to do this because there's a full resolution of all compounds, all materials, as enthalpy and entropy, from which this can all be calculated. So this is the key takeout. I'm hammering on this, because this is the change you guys must bring to go from simplistic methods to more sophisticated methods to fully understand the system and its true losses. Not only its gains, but its true losses. That means also the entropic dissipation from that system. Just as a quick result from this, and this is interesting for you to see, once again you can read the sheets at your own leisure, but these orange flows in the Sankey diagram are really the exegetic dissipation of that system. It's gone. And coming up with some unrealistic higher recycling rates of materials because of some kind of, I call them cookie point factors in models which come from somewhere, not often based on solid interconnected metal wheel physics, would not be able to predict you this loss. And that's a key message for design for recycling, because ultimately closing the loop is physically really not possible, but we can mitigate it. But we can only mitigate it if we understand the true physics behind it. And this figure actually shows that to you. Then one of the final sheets before I end off, and once again you can have a look in the detail of this. If you look at design for recycling, we've looked at exergy, but then you can also very easily now, because the simulator produces this, it's linked to LCA tools, as it was explained by my colleague Antti Roine from Metsä Outotec. Depending on where you process this, you have different footprints. And therefore one has to very, very carefully consider the whole supply chain and where it is done to ensure that the infrastructure that we are creating and the product that we are producing ultimately in that infrastructure has the lowest footprint that it can have. And it's very clear what the message from this figure is. One has to really take care of that message. And a simulator permits you to answer that in a very transparent way where the mass balance of all elements is closed. We know where all the compounds go. We know what the entropy flow in the system is. So we know also the hidden losses from the system. And by the way, therefore, we can also now easily, by button press, really get the footprint as well, which is really a small bit at the end. The real heart of the matter is the depth of that system and modeling that. So in conclusion, I come back to this drawing that I showed originally at the first sheet. Is this nexus energy, materials? Materials is also an energy flow. It's got an enthalpy value, in other words. It's got a free energy value, a Gibbs quantity calculated from the entropy and the enthalpy. But very clear from this, if we're looking at the design for recycling, we have to consider this whole figure and also understand the entropic and therefore exergy dissipation from that system, which is the orangey-red band at the outside. And if you look carefully, it's a bit of a spiral. Let's have a good look. It's actually a spiral downward. Each time we go through it, we're spiraling downward. So interestingly enough, and you can also go and check this out in the internet, you can download this interview I had with Aurubis. But then we actually discussed this very openly. Aurubis, the largest copper recycler in the world, and we discussed the inconvenient truth of the circular economy. And Aurubis, as a company, being world-class metallurgists, they know about this. And this is at the heart of what I'm trying to say here. So please have a look, because you can make a change. I think just by the mere fact that you guys are listening and have interest, the tools are there, the people are around that can help.